It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we are going to look at Chapter 13 and 14 practice problems, which have to do with waves and simple harmonic motion. Number 1. A 0.350 kilogram object attached to a spring with a spring constant of 1.30 times 10 to the negative 2 newtons per meter is free to move on a frictionless horizontal surface. If the object is released from rest at x equals 0.100 meters, find the force on it and its acceleration at 0.1 meters, 0.05, 0, and negative 0.1 meters. Let's just sketch out a picture really quick. We have a spring with a mass attached to it, and we pull the spring to the right at a distance of x equals 0.100 meters for the first part. That's how far away it is from its equilibrium position. As we can see for the first part, actually the first couple, when we pull the mass towards the right, the force that the spring is exerting on the mass is going towards the left in the opposite direction, because the spring is pulling against the mass. Let's use Hooke's law to calculate the force on the spring at each of these locations. Why don't we just make a chart really quick to help us organize our information. Whoa, where'd that go? Let's try that again. Let's try that one more time. Let's not try that anymore. Let's just make a chart together. So much for pre-planning. We'll have our different elongations on the top. We'll have 4 different ones, so let's make 4 columns. And then we'll have force and acceleration for our rows. We've got 0.100 meters, 0.500 meters, 0 meters, and negative 0.100 meters. Our first column will be the spring force, F sub s, and our second will be the acceleration, A. If we look at Hooke's law, we have F sub s equals negative k times x. All we have to do to calculate the force is just plug and chug our different x values. So for the first one, we'll show our work. F sub s is negative k, which is the spring force, negative 1.30 times 10 to the 2 newtons per meter, times x for the first part, 0.100 meters. Plug and chug, and we get a spring force to equal about negative 13 newtons. So for the first part, negative 13 newtons. For the second part, the distance is now, or the elongation is now halfway from where it was in the first part. So to calculate its spring force, we'll plug and chug at 0.5, but we're going to get half the answer, negative 6.5 newtons. When the mass is at its equilibrium position, there's no longer the force acting on it in either direction, which means the spring force is 0 newtons. And then when the mass is at negative 0.1 meters, so let's just say it's somewhere over here, to the left of its equilibrium position, the force is now, the spring force is now going towards the right, which should give us a positive answer for our spring force. When we plug in chug, F sub s, equals negative kx, we're going to get positive 13 newtons. Next, what we want to do is find the acceleration at each one of these different points. We could use Newton's second law, A equals F net over m. The object is on a frictionless horizontal surface, so the only force acting on the object after it's released is the spring force. So in this case, it would be F sub s over m. And we just have to plug in our forces for each scenario, so let's do the first one. Negative 13 newtons over the mass 0.350 kilograms. Plug in chug and we get an acceleration to equal negative 37.1 meters per second squared. And we can do the same for the next three scenarios. For the next one, we'll get half of that, negative 18.6 meters per second squared. 0 meters per second squared because there's no force acting on the mass. And then positive, that should be negative. And then positive 37.1 meters per second squared. Next question. Number 2. Find the amplitude, frequency, and period for an object vibrating at the end of a horizontal spring if the equation for its position as a function of time is x equals 0.250 m times the cosine of pi over 8t. What is the velocity and the acceleration of the object at 2 seconds? Let's write down a formula again that we're given here. X equals 0.250 meters times the cosine of pi over 8 times t for time. If we look at this formula, we know that the first part in front of the trig function, so the 0.250 meters, that represents our amplitude. So A, the amplitude, is 0.250 meters. If you look inside the cosine formula, pi over 8, that represents the angular velocity of the object, or omega. Why don't we answer the second part of the question first, which is what is the velocity and acceleration of the object at 2 seconds? I'll put this on the right side of the paper. So if you look at the velocity formula, that's v equals a omega times the sine of omega t. We already know what a and omega are. Notice for the velocity, though, there's an omega outside of the sign, so we just have to include that when we plug in chug. It's also important to remember that we want our calculators in radians for this and not in degrees. So calculators are in radians. A equals 0.250 meters times omega, let's just keep it at pi over 8. And the units are radians per second, times the sine of omega again, pi over 8, radians per second. And the time we're told is 2 seconds. So this is times 2 seconds. Plug in chug and again make sure we're in radians. And we get a velocity to equal negative 0.696 meters per second. To calculate the acceleration, we have to use our simple harmonic motion acceleration formula, which is A equals negative capital A omega squared cosine of omega t. Whoops. Again, we'll plug and chug. Negative 0.250 meters times omega squared, that's pi over 8 radians per second quantity squared, times the cosine of omega again, pi over 8 radians per second times 2 seconds. Plug and chug and we get the acceleration equal negative 0.0273 meters per second squared. All right, let's look back at the frequency and the period. I'm just going to call this letter, let's see, I don't know, let's just call it letter A. Who cares? So to get the frequency, we know that omega is equal to 2 pi f. Let's solve for f. F equals omega over 2 pi. We already know that omega is pi over 8 radians per second. So we can say F equals pi over 8 radians per second all over 2 times pi. Plug and chug and we get a frequency to equal 0.0626 hertz. To calculate the period, frequency is 1 over the period, plus letter B. Frequency is equal to 1 over the period, that's capital T, which means the period is 1 over the frequency, which gives us 1 over 0.0626 hertz. It's a 6 right there, sorry. And we get a period to equal 16.0 seconds. Next question. Looks like I'll have to erase all my tables below. If this moves. Number 3. Number 3. Using a small pendulum of length 0.170 meters, a geophysicist counts 72 complete swings in a time of 60 seconds. What is the value of G at this location? The length of the pendulum, is 0.171 meters. It completes 72 swings in 60 seconds. We can calculate its period, that's the time for one swing. So that would give us 60 seconds over 72 swings, which gives us a period of 0.83 seconds per swing. And we want to find the acceleration due to gravity at this point. Let's look at the formula we have for a pendulum and acceleration due to gravity, as well as the relationship between length and period. And that is the period equals 2 pi times the square root of the length over g. And what we want to do is find g, the acceleration due to gravity. Let's divide both sides by 2 pi first. Period over 2 pi. Why don't we square the square roots, which means we have to square everything, is equal to L over G. I guess we'll well, why don't we square what's inside the parentheses? T squared over 4 pi squared equals L over G. Let's cross multiply. GT squared equals 4 pi squared L, and then divide both sides by the period squared. G equals 4 pi squared L all over T squared. Let's plug and chug. 4 pi squared times the length, 0.171 meters, all over the period squared, 0.83 seconds squared. Plug and chug, and we get the acceleration due to gravity to equal 9.80 meters per second squared. Okay. Next question, number 4. An ambulance travels down a highway at a speed of 33.5 meters per second. Its siren is emitting sound at a frequency of 400 hertz. What frequency is heard by a passenger in a car traveling at 24.6 meters per second in the opposite direction of the ambulance as they approach each other? In other words, they're traveling towards each other in this scenario. Why don't we label a picture, because the signs are going to, the directions of the cars are going to make a difference of what signs we use for our formula. We have our observer, that's the car. So the velocity of the car, let's just say it's traveling towards the right, is 24.6 meters per second. The frequency they observe is what we're trying to calculate as a result of the ambulance traveling towards the left. The velocity of the source, 33.5 meters per second. And we know the frequency of the source is equal to 400 hertz. Let's assume that the temperature outside is at STP, which is 20 degrees Celsius, which means the speed of sound will be 343 meters per second. Okay, so let's set up our Doppler effect formula. This is for part A. We have F sub 0, the observed frequency, equals F sub s, the frequency of the source, times the speed of sound plus the speed of the observer, divided by the speed of sound minus the speed or velocity of the source. When the objects or the cars or whatever are traveling towards each other, we don't change anything in this formula. So this negative here is already built in the formula. We're going to keep it as it is. To calculate the observed frequency, all we're going to do is plug and chug. F0 equals, it's a good video game, 400 hertz times the speed of sound, 343 meters per second, plus the speed of the observer, 24.6 meters per second, divided by 343 meters per second again, minus the speed of the source, 33.5 meters per second. Plug and chug, and we get an observed frequency of 475 hertz. When they're traveling towards each other, we can see that the apparent frequency is going to increase to 475 hertz. Letter B, this time we're looking at as they pass each other. So now the source, it's still going to the left, and the observer is now going to the right. As we can see, they're traveling in opposite directions. Since they're traveling in opposite directions, we now have to negate the signs inside the formula. That gives us the observed frequency equals F sub s times V minus V0 over V plus Vs. Plug in chug, we'll skip that part, we'll plug it in our calculators, and we get 338 hertz. So just to be clear, to reiterate, when the object and the source are traveling towards each other, we don't do anything with the signs inside the formula. But when they're traveling away from each other, we have to negate the signs. Last question. Here we go. Last question. A pipe is 2.46 meters long. Determine the first and third harmonics if the pipe is closed on one end. Use 343 meters per second as the speed of sound in air at 20 degrees Celsius. So we're going to calculate the first and third harmonics. The first formula for the first harmonic, for the frequency, f sub 1, is equal to v, the speed of sound, over 4 times the length. So all we have to do is plug in chug. F1 equals 343 meters per second, all over 4 times 2.46 meters. F sub 1 equals 34.9 hertz. Second part, same thing, except now we're going to solve for the third harmonic. And F sub 3 is equal to 3 times F sub 1. F sub 3 is equal to 3 times 34.9 hertz. And we get F sub 3 to equal 105 hertz. And that's it. Thank you for watching, and I hope you found this video useful. And I'll see you next time. See ya.